Welcome to Properties of Integers. In our last Properties of Integers video, we covered induction, recursion, and we introduced integer division. In this video, we will continue with integer division and division algorithm. We'll talk about bases, we'll go over the Euclidean algorithm, and a quick review of the fundamental theorem of arithmetic. Our first topic is integer division. In our last video, we discussed that this chapter deals with properties of integers, so all of our theorems, our results, our methods, our algorithms are going to apply to integers. And while at times it will be tempting to do a division, when we divide one integer by another, we risk the possibility of introducing a non-integer, which would be a mistake. Fortunately, we have this definition here of divisibility, which will allow us to work with the concept of division without actually performing the operation of division. So our definition says, if a and b are integers and b is not equal to 0, we say b divides a, and we write b divides a. If there is an integer n such that a equals b times n, we say b is a divisor of a, or a is a multiple of b. We also looked at theorem 4.3 on your handout, and this is where we will start today. Theorem 4.3, part F, A divides B and C divides A implies A divides any linear combination of A and B is proved in the book. Theorem 4.3, part C, A divides B and B divides C implies A divides C is proved in our last video. We are going to look at theorem 4.3 part E. If x equals y plus z for some integers x, y, and z, and a divides two of the three integers x, y, and z, then a divides the remaining integer. We are going to look at the case where a divides x and a divides y. So a divides x over here and a divides y over here. The case of a divides x and a divides z is totally analogous. The case where a divides y and z I will leave to you. I start by looking at my givens that a divides x and a divides y. Well, if a divides x, that implies x is equal to a to the n for some integer n. And if a divides y, then that implies y equals am for some integer m. And then I look to see what I need to prove. If I want to show that a divides z, I need to find an integer s such that z is equal to as. To help me find this s, I'm going to look and see what other information I can use, what other information I am given. So I'm given this line here if x is equal to y plus z. So I'm going to start my proof with my steps on the left and justification on the right. Now I can also rewrite my y as a times some integer m, the way I did up here. And my justification is I am given that a divides y. I can also rewrite my x as a times some integer n because I was given that a divides x. And again, I kind of wrote that up here. So with a little bit of algebra, I could get that z equals a times n minus m. Then I have that z equals a times s, where s is the integer we get when we subtract n minus m. And here I am done with my proof because a divides z by definition of divisibility. Another example from your book, if a, b, and c are integers and 31 divides 5a plus 7b plus 11c, prove that 31 divides 21a plus 17b plus 9c. When trying to figure out where to start, we can look at what we have so far. We've covered the definition of divisibility, and we've covered theorem 4.3. So we'll look at theorem 4.3 And there are, if you look at parts F and part G, they deal with linear combinations. And since our problem here talks about linear combinations of A, B, and C, we're going to look at part G, theorem 4.3 part G. So theorem 4.3G is right over here, and it says for I between 1 through n, let C sub I be integers. If A divides each C sub I, then A will divide any linear combination of C sub I. Essentially, the linear combination is C1 x1, where x is an integer, plus C2 x2, where x2 is an integer, etc., up to Cn x of n, where x of n is an integer. So looking again at our problem, we have 31 divides, this linear combination of A, B, and C, as well as this linear combination of A, B, and C. And we also know, since 31 divides 31, it'll divide any linear combination of 31 times A, 31 times B, and 31 times C. Again, that's from theorem 4.3. Now we have 31 dividing 31A plus 31B plus 31C, and we also know from our problem that 31 divides 5A plus 7B plus 11C. So by theorem 4.3, 31 should divide any linear combination of this number and this number. Again, 31 divides any linear combination of 31A plus 31B plus 31C and 5A plus 7B plus 11C. Again, this should be 31. In particular, we can choose the linear combination 31A plus 31B plus 31C minus 2 times A plus 5A plus 7B plus 11C. The significance of this particular linear combination, where 31A plus 31B plus 31C is multiplied by 1 and then added to 5A plus 7B plus 11C multiplied by -2, is that when you work this out algebraically, you get the 21A plus 17B plus 9C that you were looking for, and then you're done. Again, this example relied heavily on theorem 4.3 part G. Another example, do any of the 12 numbers below sum to exactly 500, and the 12 numbers are 144, 336, 30, 66, 138, 162, 318, 54, 84, 288, 126, and 456. This is also a problem in your book. It's more wordy, described as some contest at a grocery store or something. Since this question is about sums, again, we'll think about theorem 4.3 because that talks about linear combinations. In particular, we're going to consider linear combinations of the 12 numbers. In terms of linear combinations in the original question, do any of the 12 numbers sum to exactly 500? Essentially what we're doing to make it into this question is we'll limit our x sub I to be either 0 or 1. And then the question is there a linear combination where the x sub I is 0 or 1, where this sum equals 500? Now I'm going to note that 6 divides these 12 numbers. So 6 should divide the linear combination of these 12 numbers. However, 6 does not divide 500. So by theorem 4.3, there is no linear combination that equals 500. And that's any linear combination, even without the restriction of x sub I equals 0, 1. But if there's no linear combination, then certainly there's no combination with just x sub I equals 0, 1. So no subset of these numbers will sum to exactly 500. When I do this problem, I often get the question, since I noted that 6 divided all of the 12 numbers, but it does not divide 500, I often get the question, well, what about 2? Because 2 divides all of the 12 numbers, and it also divides 500. This here should have been 2 divides 500. But look at theorem 4.3 carefully. It says that 2 divides the 12 numbers, it will divide any linear combination of the 12 numbers. It does not say that if 2 divides 500, 2 must be a linear combination. That's actually reading the logic the wrong way. And in fact, we talked about this in chapter 2. It's a flawed attempt to argue the converse. Do you remember that was the trap? So again, theorem 4.3 says that if 2 divides the 12 numbers, it will divide any linear combination. It does not say if 2 divides a number, that number must be a linear combination. So there is one more example that's in the text, and I'll point you to it. There is a clever but easy to follow proof. There are infinitely many primes. Next, we will talk about the division algorithm, which comes from the theorem that says if a and b are integers with b greater than 0, then there exist unique integers q and r with a equal to q times b plus r, where r is greater than or equal to 0 and less than b. So this is a fact you've been familiar with since you learned how to divide in 2nd or 3rd grade. So basically, if you have two integers, a is equal to some quotient times b plus a remainder. The proof is not constructive. In other words, it does not tell you how to find q and b, but the text supplies you an algorithm to find q and b, and basically that algorithm is to treat division as repeated subtraction. If you recall from 3rd grade or 2nd grade, when you learned how to multiply, multiplication was often defined as repeated addition. Well, here we're going to define division as repeated subtraction. So our example of the division algorithm is a is equal to 170. We're going to divide it by b, which is equal to 11. So we start by counting how many times we can subtract 11 from 170. The first time we subtract 11 from 170, we get 159. We subtract 11 another time, so our count increases by 1 and we get 148. We keep going. After 5 times, we have 115. After 12 subtractions, we have 38. And finally, after 15 subtractions, we have 5, which is now 5 is greater than or equal to 0, but it's less than 11. So our final result is 170 equals 15 times 11 plus 5. So the significance of the division algorithm is that division can be viewed as repeated subtraction. Applications, we'll have a couple of applications, but the first one we'll look at is representing integers in different bases. Just to remind you about bases, kind of to get a start, is we'll consider the number 456 base 10. So this is basically the number 400, no pun intended, this is the number 456. And what we consider this going from the rightmost digit, those are our ones digit. In other words, it's 10 to the 0. This here, the second from the right, was our tens digit, which is 10 to the 1. And our last one here is our hundreds, which is 10 squared. So essentially what we have is 4 times 10 squared plus 5 times 10 to the 1 plus 6 times 10 to the 0. And that's how we get the 456. We can write numbers in other bases, such as the number 100, base 2, and what we would have here is this would be our 2 to the 0 power, 2 to the 1, and 2 squared. So this would be 1 times 2 squared plus 0 times 2 to the 1 plus 0 times 2 to the 0. So this number is equal to 4. So this is the representation in base 2 of our normal number 4, base 10. So we're going to use our division algorithm to convert bases, and we'll basically use successive remainders to convert bases. So for our example, we're going to write 137 in base 2 and then in base 16. So again, we're going to use successive remainders. So we're going to divide 137 by 2, and we'll get 68 with the remainder 1. That's our first remainder. Then we'll divide by 2 again, and we'll get 34. At this point, we have a remainder of 0. We continue dividing 34 by 2s, then 17 by 2, where we get a remainder of 1, 8 by 2, 4 by 2, so we finish off, that goes in twice, remainder 0, and then finally goes in once, again remainder 0. So here we have our answer. 137 in base 2 is the 1, 0, 0, 0, 1, 0, 0, 1. So again, I'll write that. You're reading from the bottom up. So it's 1, 0, 0, 0, 1, 0, 0, 1. To check that answer, you would have 1 times 2 to the 0 plus, this is our 2 to the 1 term, this is our 2 squared term, and then 1 times 2 to the 3rd. Here we have 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th. So we have 1 times 2 to the 7th, which is 128, plus 0 times 64, plus 0 times 32, plus 0 times 16, plus 1 times 8, 2 to the 3rd, plus 0 times 4, plus 0 times 2, plus 1, which will give us 137. In computer science, we represent numbers in binary, which is base 2. So here, using a 4-bit representation, you can represent the numbers 1 through 7. But we also need negative numbers so that we can use an adder to do our subtraction. And that's where 2's complement comes in. It helps, 2's complement is what we use to represent negative numbers. The way we find a 2's complement, or a negative of a number, is we start with the binary representation, then we interchange, not interchange, but interchange zeros and ones. This is known as the 1's complement, and then we add 1. So I fixed this to say interchange. Our example is going to be 6. A binary representation is 0, 1, 1, 0. Now we interchange the zeros and ones, so our 0 becomes 1 and our 1s become 0s. That's the 1's complement. Last, we add 1 to our 1's complement to get our 2's complement. And just to show you how the adding 1 works, if we have 1, 0, 0, 1 as our 1's complement, we add 1. So going from right to left, our 1 plus 1 here, 1 plus 1 is going to be 2. In binary, that's 1, 0, so we have to carry the 1. Then we're going to add the 1 to the 0 and 0. That'll give us 1. We're going to add the 0 and the 0. That'll give us 0. And last, we add the 1 to the 0. That'll get us 1. So that's our 2's complement. And if I did this correctly, when I add our 2's complement, our negative 6 to our 6, I should get 0. So let me do that on the side here. I'm going to have 6 plus my negative 6. And my 2's complement notation, I have 0, 1, 1, 0. That's my 6. And I'm going to add 1, 0, 1, 0. Okay, so my 0 plus 0 gives me 0. My 1 plus 1 gives me 1, 0 in binary, so I'm going to put the 0 here, carry the 1. Then I have 1 plus 0. Again, that's 2, so that's 1, 0 in binary, so I need to carry the 1. And then last I have the 1 and the 0 and the 1, which is 2, so again, that's 1, 0. But at this point, because I'm representing my integers with 4 bits, I drop the 5th bit and I have 0, 0, 0. No matter what size pattern, no matter how many bits we use, the size of the integer that can be represented is limited, and when we exceed this size, an overflow error occurs. So looking at the 4-bit 2's complement representations, I have the positive numbers, the positive numbers here and the negative numbers here. One thing you'll notice is that all the positive numbers have the 0 in the this leftmost bit, whereas the negative numbers have a 1 in the leftmost bit. As a result, also, the positive numbers can only go to 7. We can't represent positive 8 with only 4 bits in 2's complement. The example of overflow, if we add 117 to 88, so 117 is 0, 1, 1, 1, 0, 1, 0, 1 in 2's complement. 88 is 0, 1, 0, 1, 1, 0, 0, 0 in 2's complement. Again, we're going to add the 1 and the 0 is 1, 0, 0 is 0, 1, 0 is 1, 0, 1 is 1, 1, 1 is 2, so we're going to carry the 1, 1, 1 is 2, so we carry the 1, 1, 1, 1 is 3, so we have 11. And then if you notice what happened is we have our two positive integers, and when we add them together, we end up with a negative integer. So what that tells us is that an overflow error has occurred. In other words, the 117 plus 88 gives us a number that we cannot represent, that we need another digit to represent in 2's complement. So we've gone through bases, and our next topic is the Euclidean algorithm. First, we have some definitions. For integers a and b, a positive integer c is said to be a common divisor of a and b if c divides a and c divides b. And we have this notation with the straight line. Okay, if either a does not equal 0 or if b does not equal 0, then c, a positive integer, is called a greatest common divisor. The notation is c is equal to GCD of a and b if c is a common divisor, and for any common divisor d of a and b, we have d divides c. So these two definitions are consistent with what you learned in 2nd or 3rd grade. So our theorem is, for all integers a and b, there exists a unique positive integer c that is the greatest common divisor of a and b. So again, this is consistent with what you've learned in elementary school. The proof is in the text. The proof is constructive and uses the division algorithm. And from this proof, we note not only does the greatest common divisor of a and b exist, but the greatest common divisor of b is also the smallest possible integer we can write as a linear combination of a and b. So actually, we do use this fact over here quite a lot, the linear combination. And I need to squeeze in one more definition. Integers are called relatively prime when their greatest common divisor is 1, and there exists integer x and y such that ax plus by equals 1. Okay, this is what the Euclidean algorithm looks like. This is how you find the greatest common divisor. And I do realize in elementary school you learned how to find the greatest common divisor by factoring and finding the greatest common, getting all the common factors. But this is different, and we're going to use this differently because we can solve other problems that you didn't learn how to solve in elementary. So essentially what we're going to be doing are these repeated divisions, finding Q and R, which we got from the division algorithm, and we're just going to keep moving them over and doing repeating this over and over. And finally, we'll end up with the greatest common divisor. Probably the easiest way to show you this is with an example. So we're going to find the greatest common divisor of 2,689 and also 4,001. And again, I know you know how to do this from elementary school, but again, we're going to use this technique because then you can solve different types of problems that you couldn't solve in elementary. So we'll start with, we'll start with 4,000 is equal to 1 times 2,689 plus a remainder of 1,312. Now we're going to move this over here and this over here because that's essentially this part of the step. So we're going to have 2,689 is equal to 2 times 1,312. 12 plus remainder 65. And again, now we move our remainders over, this over here and this over here. So we have 1, 3, 1, 2 is equal to 20 times, now we move the 65 plus remainder 12. Again, we move the 65 over, is equal to something times 12, which is 5 times 12 plus remainder 5. We remove the 12 over, is equal to, we have this 5 times 2 plus 2. Move over the 5 is equal to 2 times 2 plus 1. And now we have 2 equals 2 times 1 plus 0, and backing up 1. This last remainder is our greatest common divisor. So I cleaned this up a little bit so you could see things without all the arrows. But I'm going to draw those arrows one more time. Essentially, you just keep moving these remainders over, shifting them over as the division algorithm tells you to. And once you get to a 1 over here on the remainder, you're done. So now again, we're going to start with a clean copy so that I can kind of take these steps in reverse. So I'm going to start at the bottom, and I'm going to find the linear combination of 2689 and 4001 that will give me 1. Obviously, there's going to be some negative numbers in here. But I'm going to rewrite this equation, this last equation here, as 1 is equal to 5 minus 2 times 2. And you might guess that this 1 here is our greatest common divisor, and we're on our way to writing some sort of linear equation. And now I'm going to look at my next line, and I'm going to substitute this remainder for this number here. So I'm going to have that 1 is equal to 5 minus 2, and I'm going to substitute again for this 2 here. I'm going to substitute 12 minus 2 times 5. So I'm going to have 12 minus 2 times 5. Then I'm going to do some regrouping, and I'm going to say that's equal to 5 times 5, because I have this 5 here, plus I have another 4 5s, right? That minus 2 times 5. And then I am going to still be left with my 2 times 12. In my next equation, my remainder is 5. So I'm going to substitute it for one of these 5s here. So again, for this 5, I am going to substitute 65 minus 5 times 12. So that'll give me, oops, let me write this in black, 5 times 65 minus 5 times 12, and then I still have my, from over here, I still have my minus 2 times 12, and again I'm going to regroup my terms because I want to combine these 12s with these 12s, so I'll get 5 times 65 minus 27 times 12. Working my way up, so now I want to substitute this 12 in my equation with the 12 here, the remainder. So again, I look at the remainder to see what I can substitute. So for this 12, I am going to substitute the 1312 minus 20 times 65. So that'll give me 5 times 65 minus 27 times 1312 minus 20 times 65. And now again, I'm going to group my 65s together, and I'm going to get 545 times 65 minus 27 times 1,312. Maybe I should write a multiplication. Now I'm going to look at my 65, and I see a 65 here. So this 65 I am going to replace with 2689 minus 2 times 1312. So that'll give me, this is getting really big, but 545 times 2689 minus 2 times 1312 minus 27 times 1312. I'm going to combine my 1312s, and I get 545 times 2689 minus 1117 times 1312. And last, I am going to substitute 1312, which I see right over here, and I'm going to substitute this for it. So I am going to get 545 times 2689 minus 117, oops, with another 1, times 4,000 minus 2689, which will give me 1,600, 62 times 2689, I should erase that, minus 1117 times 4001. Again, that's my linear combination. Okay, I wrote it one more time to clean it up. Another example, the greatest common divisor of 8n plus 3 and 5n plus 2. So I'll start 8n plus 3 is equal to 1 times 5n plus 2, remainder 3n plus 1. Then I'll get 5n plus 2 is equal to 1 times 3n plus 1 plus 2n plus 1. I'll have 3n plus 1 is equal to 1 times 2n plus 1 plus n. And then 2n plus 1 is equal to 2 times n plus 1. So the greatest common divisor of 8n plus 3 and 5n plus 2 is equal to 1, which is kind of amazing. And if you do this algorithm backwards, you'll find that 8n plus 3 times minus 5 plus 5n plus 2 times 8 is equal to 1. And also 1 then is a linear combination, and it's the smallest positive integer that can be written as the linear combination of these two numbers. So our next example is the problem, are there positive integer solutions to the equation 249 equals 3.3y plus 2.9x? So the interesting thing about this equation is it's one equation and two unknowns. So as it is, we can't do this because we don't solve two unknowns with one equation. However, if we can convert this to an equation with integers, we can work this. So our first step is going to be to multiply everything by 10. So we're going to have 2490 equals 33y plus 29x. So for now, just go with me on this. We're going to find the greatest common divisor of 33 and 29, and you'll see why later. So we're going to use our Euclidean algorithm, and we get 33 equals 1 times 29 plus 4, and 29 is equal to 7 times 4 plus 1. So this is our greatest common divisor. And then we work backwards, and we're going to have 1 is equal to 29 minus 7 times 4, which is equal to, and then but then the next thing is we're going to substitute this 4, and we're going to have equals 29 minus 7 times 33 minus 29. So then we're going to have 8 times 29 minus 7 times 33. So we have 1, let me actually write it over here. We have 1 equals 8 times 29 minus 7 times 33. So the whole reason for doing this is to find a solution to this equation here. But if I multiply everything by 2,000, so multiply the whole equation by 2,490, what I can get is 2,490 is equal to 19920 times 29 minus 17430 times 33. So now I have a solution with integers. However, they're not positive integers, but so far I'm doing pretty well. And again, the thing that helped us go from this step to this step is that the greatest common divisor that was a multiple of 2490. If it were not a multiple, this would not have worked. We would have been stuck. Okay, so to get positive integer solutions, we're going to introduce a couple of variables that'll allow us to shift things around until things are positive. So we're going to take this 19920 and we're going to subtract 33k, and then over here I'm going to take the 17,430 and add 29k. So essentially we haven't changed the equation because here we're subtracting 29 times minus 33k, and here we're adding it back, the 33 times 29k. So here we have our 29 times some value and our 33 times some value. We're going to call this our x, and we want it to be greater than or equal to 0. This is our y. We want it to be greater than or equal to 0. And let me just write this here. X is equal to 11920 minus 33k, and 1 is minus 17430 plus 29k. So when I look at this equation of x, that gives me a restriction on k, which is that k, let's see, I have 0 is less than or equal to 1992033k. So then this becomes negative over here, which means k is less than or equal to 11920 over 33. Similarly, if I look at y, that will give me the restriction that k is greater than 17430 divided by 29. Actually, that's greater than or equal. Now, because we want k to be an integer, essentially what we have is k is going to be some number between 601 and 603.6, which means that k can equal to 602, in which case x is equal to 54 and y is equal to 28, or k is equal to 603, in which case x is equal to 21 and y is equal to 57. So here is our solution for x and y. Our last theorem for this section is, if a, b, and c are positive integers, the Diophantine equation ax plus by equals c has integer solutions x equals x naught, y equals y naught, if and only if the greatest common divisor of a and b divides c. You can look at our last example to get some insight into this, where we were looking at solutions to the equation 2490 equals 33y plus 29x. So again, here's our Diophantine equation where ax plus by equals c. In this case, c is 2490. We found the greatest common divisor of 33 and 29, which happened to be 1. And we wrote the greatest common divisor as a linear combination of 29 and 33. And then last, because the greatest common divisor divided C, which is what this is here, if and only if the greatest common divisor of A and B divides C, because it does divide it, fortunately it was 1, but because it does divide it, we were able then to multiply by some number, in this case it happened to be 2490, and then find the integer solutions, which was 1920 and 17430. And then we did some other manipulations in order to have, and this was a minus, in order to have positive solutions. So our last example of the Euclidean algorithm, we have the problem of, we have two unmarked containers. One holds exactly 17 ounces, the other holds exactly 55 ounces. How can we measure exactly 1 ounce? We start by using the Euclidean algorithm to find the greatest common divisor. So we're going to have 55 is equal to 3 times 17 plus 4. Then 17 is equal to 4 times 4 plus 1. So we know 1 is our greatest common divisor of 17 and 55. So that's good news, because then that means we can solve any Diophantine equation. We use the steps backwards. So we get 1 is equal to 17 minus 4 times 4, which is equal to 17 minus 4 times 55 minus 3 times 17. So then we get 13 times 17 minus 4 times 55. So here is our answer. We just need to understand it. But essentially, this is telling us we're going to fill the 17-ounce container 13 times, and something about maybe emptying, because of -4, our 55-ounce container 4 times. So let's take a look at the interpretation. So we fill the 17-ounce container 13 times, and basically every time we fill it, we empty it into the larger container. So the first 12 times we're emptying it into the large container, and the large container, every time it's full, each time it is full, it's also emptied. So again, just kind of looking at the 12th time that we've filled the 17-ounce container, after 12 times, we've filled it up a total of 204 ounces. So essentially, it's emptied, it's filled the 55-ounce container 3 times. So I have that here. After the 55-ounce container is filled 3 times, so 165 ounces have gone in. Then on the 12th time, we have the 204 minus the 165, so after the 12th time, there's 39 ounces left in the large container. It hasn't been filled yet, so it's still not dumped out. So then the 13th time, the 17-ounce container is filled. We're going to have the 39 plus 17 ounces, but that's 56 ounces. So only 16 ounces are going to be able to be poured into the 55-ounce container, and 1 ounce will be left in the smaller jar. And that's our solution. Now that we've completed Euclidean algorithm, one last topic is the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic is something you've known since elementary, but it basically tells us that every integer greater than 1 can be written as a product of primes uniquely up to the order of primes. So basically it just tells you every number has a prime factorization, and that prime factorization is unique. There's a proof of existence. Uniqueness is in the text. Here's the proof of existence. If existence is not true, then let m greater than 1 be the smallest integer not expressible as a product of primes. Since m is not prime, we can write m is equal to m1, m2, where m1 and 2 are between 1 and m. But then m1 and m2 can be written as a product of primes because they are less than m, and m is supposed to be the smallest number. Consequently, m is equal to m1 times m2 and can obtain a prime factorization. And this is where we will finish. So we've covered the induction, recursion, integer division, and division algorithm, bases, the Euclidean algorithm, and the fundamental theorem of arithmetic. Thank you for listening, and I'll see you in class.